Now in this lecture we'll answer two questions. In the first question we'll find out the area of this circle that is inscribed by this trapezoid ABCD, and in the second question we'll find out the length of this line segment QB that is equals to x. So to start with the first question, in the drawing we have a circle. This circle is inscribed by this trapezoid ABCD. A trapezoid is a quadrilateral with one pair of parallel sides. Repeat again. A trapezoid is a quadrilateral with one pair of parallel sides. In this trapezoid ABCD, side AD is parallel to side BC. So in addition, we know that this is line segment AM, that is equal to A units in its length. This is line segment MB, that is equals to B units in its length. Again, our mission is to find out the area of this circle that is inscribed by this trapezoid ABCD. So first of all, we define the center of this circle. This point is point O. We define the point of tendency obtained AD with this circle. This point is point P. And we define the point of tendency obtained BC with this circle. This point is point Q. So here we can implement rule 2. I'll repeat quickly on rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. In the drawing we have a circle. This is the common external point, point P. From this common external point, point P, we have tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. So we can implement rule 2 in our drawing. In our drawing, if we focus on this current external point, point A, on this current external point, point A, we have two tangents to this circle, tangent AM and tangent AP. And according to rule 2, they are equal to each other. That is to say, AM equals to AP. But AM is 8, therefore AP must be also equal to A units in its length. Likewise, we focus on this common external point, point B. From this common external point, point B, we have two tangents to this circle, tangent BM and tangent BQ. And according to rule 2, they are equal to each other. That is to say, BM equals to BQ. But BM equals to B units in its length, according to what is given as the question. Therefore, BQ must be also equal to B units in its length. So this is tangent BQ, that is equal to B units in its length. In the next step, we'll join points O and Q together by a straight line. Point O is the center of the circle, point Q is the point of the circle itself, therefore OQ is the radius of this circle. We define the radius of this circle as x, therefore OQ equals to x, this is the radius of this circle. And because of the fact that the radius OQ is 1 to point Q, that is the point of tendency of tangent BC with this circle, and whenever you have a radius that is known to the point of tendency, then tangent BC will be perpendicular to the radius OQ. If BC is perpendicular to OQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and P together by a straight line. OP is of course the radius of this circle that is equal to x, and because of the fact that the radius OP that is equal to x, the radius OP is known to point P, that is the point of tendency of tangent AD with this circle, and whenever your radius that is known to the point of tendency, then tangent AD will be perpendicular to the radius PO. If AD is perpendicular to PO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. In the next step, we will do a construction. That is to say, from this point A, we will go perpendicular on BC. Again, from point A, we will go perpendicular on BC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and BC. This point is point N. By doing this construction, we created here those two angles. Those two angles are defined as one-sided interior angles, and those two one-sided interior angles are located between the parallel lines AD and BC. Why side AD is parallel to side BC? Because of the fact that ABCD is a trapezoid. Okay, so those two one-sided angles are located between the parallel lines AD and BC, and therefore, according to rule 17, the sum of those two one-sided angles that are located between the parallel lines AB and BC must be equal to 180 degrees. So I'll repeat quickly on rule 17. According to rule 17, the sum of one-sided interior angles between two parallel lines is equal to 180 degrees. In the drawing, we have line A that is parallel to line B. The red line C intersects with those two parallel lines A and B at those 2 points. Those are angles alpha and beta that are defined as one-sided interior angles, and because of the fact that those two one-sided interior angles are located between those two parallel lines A and B, the sum of those two one-sided interior angles must be equal to 180 degrees. That is to say, alpha plus beta is equal to 180 degrees. So actually, I already implemented rule 17 in our drawing, so I already mentioned before, because of the fact that those two one-sided interior angles are located between the parallel lines AD and BC, therefore according to rule 17, the sum of those two one-sided interior angles must be equal to 180 degrees. So 90 degrees plus the size of this angle, in total the sum of those two angles must be equal to 180 degrees according to rule 17. Therefore, the size of this missing angle must be equal to 90 degrees. So this angle equals to 90 degrees according to rule 17. In the next step, we will do another construction. That is to say, from this point O, we will go perpendicular on AN. Again, from point O, we will go perpendicular on AN. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AN. From point O and AN, this point is point T. By doing this construction, we're going to do this small quadrilateral APOT. Inside this small quadrilateral APOT, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that said that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. Likewise, inside the lower quadrilateral TOQN, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total it must be equal to 360 degrees, according to the same rule that I mentioned, that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So actually, the big angle POQ in total is equal to 90 degrees plus 90 degrees, that is 180 degrees. So I'll write it down. The size of the big angle POQ is equal to 180 degrees. And we know that any angle that is equal to 180 degrees in size, it is a straight line. Therefore, line segment POQ is a straight line. If line segment POQ is a straight line, then PQ is also a straight line. PQ is a straight line. And therefore, shape APQN, this shape APQN consists of 4 sides. 1, 2, 3, 4. Shape APQN consists of 4 sides. We know that any shape that consists of 4 sides, it is a quadrilateral. Therefore, shape APQN is a quadrilateral. And we know that in quadrilateral APQN, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be this rectangle, if not a square. So we refer to this quadrilateral APQN as a rectangle because it has 4 right angles. So I write it down. So this is quadrilateral APQN, that is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle APQN, side AP must be equal to the opposite side NQ. But AP is A, therefore NQ must be also equal to A units in its length. Likewise, according to the same rule, in the same rectangle APQN, side PQ must be equal to the opposite side AN. PQ in total equals to x plus x, that is 2x, therefore the opposite side AN must be also equal to 2x units in its length. What is the length of this missing 9797 BN? From the drawing it is very easy to see that BN equals to BQ minus NQ. So I write it down. BN equals to BQ minus NQ. So BN equals to BQ. BQ is B minus NQ. NQ is A. So in total, BN equals to B minus A units in its length. BN equals to B minus A units. So in the next step, I'll copy this right triangle A and B in the equation. We will implement the Pythagoras theorem on this right triangle A and B. The hypotenuse AB equals to A plus B, Bn equals to B minus A, and An equals to 2x. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the relation for Pythagoras theorem. So actually, this is the right triangle A and B that are going from the original drawing, and this right triangle A and B according to the Pythagoras theorem. AB squared, that is the square of the hypotenuse, equals to AN squared plus BN squared. So I'll write it down. So AB squared, that is the square of the hypotenuse, is equal to AN squared plus Bn squared. AB is B plus A, therefore, or A plus B, therefore, AB squared is A plus B squared. And it is equal to AN squared. AN is 2x, therefore AN squared is 2x squared. Plus Bn squared. Bn is B minus A, therefore Bn squared is B minus A squared. So in total, if we found out that A plus B squared equals to 2x squared plus B minus A squared. We will open the brackets on both sides of this equation and you get that A plus B squared equals to A squared plus B squared plus 2 times A times B, and it is equal to 2x squared. 2x squared is 4x squared plus B minus A squared. B minus A squared equals to B squared plus A squared minus 2 times A times B. So here we have A squared on both sides of this equation, so A squared gets cancelled. And you have B squared also from on both sides of this equation, so B squared also gets cancelled. After I cancel those two expressions, in this side of the equation we left only with 2AB. On the other side of this equation we left with 4x squared minus 2ab. So in total, if we found out that two ab equals to 4x squared minus 2ab. So here we add 2ab to this equation. And we get that 2ab plus 2ab is 4ab. So 4ab equals to 4x squared. So here we will divide this equation by 4. And we get that 4ab over 4 is ab equals to 4x squared over 4 is x squared. So in total, we found out that x squared equals to ab. Our mission is to find out the area of this circle. So actually we know that the area of any circle is equal to pi times the radius of the circle squared. Repeat again, the area of any circle equals to pi times the radius of the circle squared. Therefore, the area of this circle must be equal to pi times the radius of this circle squared. So it is pi times the radius of this circle. The radius of this circle is x. Therefore, the radius squared is x squared. So in total, we found out that the area of our circle equals to pi x squared. But we just right now found out that x squared equals to ab. Therefore, we substitute x squared here by ab, and we get that the area of the circle is equal to pi times ab. So, found out quickly that the area of this circle, that is the area that we are looking for, it is equal to pi times AB square units. This is the answer to the question. Repeat again, we found out that the area of this circle is equal to pi times AB square units. We finished with the first question. In the next step, I'll present to you the second question, and we'll solve the second question of this lecture. Our mission in this second question is to find out the length of this line segment QB is equals to x. We have to find out the value of x. So in the drawing we have a semicircle, line segment AB or side AB equals to 30 units in its length. AB actually is the diameter of this semicircle. Note that the diameter of this semicircle equals to 30 units in its length. Therefore, the radius of this semicircle must be equal to half of it. That is to say, the radius must be equal to 30 over 2, that is 15. So I write it down. The radius of this semicircle must be equal to 15 units in its length. In addition, you know that this is a chord AP or line segment AP that equals to 10 units in its length. This is a chord PQ that is also equals to 10 units in its length. Again, our mission is to find out the length of this line segment QB that is equals to x. We have to find out the value of x. So first of all, we define this, the center of this semicircle. This point is point O. So what is the definition of price at OA? Let's say at OA starts from point O, that is the center of the semicircle, and that's at point A, that is a point on the semicircle itself. So this is exactly the definition of a radius. Therefore, OA is the radius of this semicircle, that is equal to 15 units in its length. Likewise, OB is also the radius of this semicircle, that is equal to 15 units. In the next step, we will join points O and P together by straight line. So point O is the center of this semicircle, point P is the point of the semicircle itself. Therefore, OP is the radius of this semicircle, that is equal to 15 units in its length. In the next step, we will complete this semicircle to a circle. And we will extend the radius PO by a straight line until it touches the circle. And we will define the touching point of the extended radius PO with this circle. This point is point M. OM is of course the radius of this circle, that is equal to 15 units in its length. In the next step, we will join points M and B together by a straight line. And we will prove that this triangle APO can go into this triangle MOB. So we prove that those two triangles can go into each other. But before that, those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if we define this angle as theta, then this angle must be also equal to theta. So those two angles are equal to each other into the one dimensions. So in the next step, we prove that those two triangles can go into each other. So this is triangle APO. And we will prove that it's going to length to this triangle OMB. Why those two triangles can go into each other? First of all, side PO of this triangle APO is equal to side OM of this triangle OMB. Well, they are both the radii of the circle, therefore they are equal to each other. So I write it down. Side PO of triangle APO is equal to side OM of triangle OMB. They are both the radii of the circle, that is equal to 15 units in its length, therefore they are equal to each other. Okay. In addition, those angles are defined as vertex angles, and we know that vertex angles are equal to each other. So this is angle AOP in triangle AOP. And it is equal to this angle, that is actually angle MOB in triangle OMB. Angle AOP equals to angle MOB, they are both equal to theta, therefore they are equal to each other. Actually they are equal to each other according to the rule that vertex angles are equal to each other. And finally, side AO of this triangle AOP is equal to side OB of this triangle OMB. They are both the area of the circle, and therefore they are equal to each other. So I write it down. Side OA of triangle AOP equals to side OB of triangle MOB. So both the area of the circle is equal to 15 units in its length, and therefore they are equal to each other. So actually proved that this triangle AOP can go to this triangle OMB according to side angle side rule. What is side angle side rule? We actually proved that those two sides and the angle that is included between those two sides, this angle of this triangle APO, correspondingly equal to those two sides and the angle that is included between those two sides, that is also angle theta, of triangle MOB. Therefore, those two triangles can go into each other according to side angle side rule. So I write it down. Actually proved the triangle APO congruent, this is the sign of congruent, to triangle OMB according to side angle side rule. And from the fact that those two triangles can go into each other, we derive that side PA of triangle APO is equal to side BM of this triangle OMB. So I write it down. We derive that PA equals to BM. PA equals to BM according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the corresponding angles, that is to say PA and BM, must be also equal to each other. Okay. But it is given us the question that PA equals to 10 units. So we can write here that PA equals to 10. And from this equation 10 equals to PA equals to BM, we will derive that BM is also equal to 10 units in its length. This is side BM, that is equal to 10 units in its length. This is chord PM. Chord PM passes through point O, that is the center of this circle, and we know that any chord that passes through the center of the circle must be the diameter of the circle. So PM is the diameter of this circle. So I'll copy this semicircle with the diameter PM, and we will analyze this semicircle. So this is the semicircle with the diameter PM that I copied from the original drawing. PQ, chord PQ or line segment PQ equals to 10 units, exactly like line segment BM that is also equal to 10 units in its length. So in the next step we will extend those two line segments that are equal to each other in their lengths until they intersect with each other. This is the intersection point or the touching point. We will define the intersection point of the extended line segment PQ with the extended line segment MB. This point is point E. So by doing this construction, we can develop two new line segments PE and ME. And actually we have the rule that if you extend two line segments that are equal to each other in their lengths, then the new line segments that will be created must be also equal to each other in their lengths. Again, when you extend two line segments that are equal to each other in their lengths, then the new line segment that will be created must be also equal to each other in their lengths. That is to say, the new line segments are EP and EM. So EP must be equal to EM according to the new rule. EP equals to EM. So, and this is triangle PEM. So in triangle EPM, side EP equals to side EM. And therefore, this triangle EPM is an isosceles triangle. Those two angles, the base of the isosceles triangle is PM. Therefore, those two angles are defined as the angles of the bases, and they must be equal to each other. Anyway, I will prove that those two angles are equal to each other, according to the rule that in front of equal sides in the triangle there are equal angles. So we know that EP equals to EM, according to the new rule. In front of this side EP we have this angle, that's actually angle EMP, and in front of this side EM we have this angle, that's actually angle MPE. And because of the fact that those two angles are located in front of those two equal sides, they must be equal to each other in their sizes. And again, because of the fact that those two angles are located in front of those two equal sides, they must be also equal to each other in their sizes. So if the size of this angle is beta, then the size of this angle must be also equal to beta. So in the next step, I will complete this semicircle to a circle. So in the drawing, we have quadrilateral QBMP. This is quadrilateral PQBM. This quadrilateral PQBM is inscribed by this circle. So here we can implement rule 16. So I can quickly rule 16. If a quadrilateral is inscribed by a circle, then the sum of its two opposite angles is equal to 180 degrees. So in the drawing we have, this is quadrilateral ABCD, and it is described by this circle, and according to this rule, rule 16, the sum of its two opposite angles is equal to 180 degrees. Those are the two opposite angles of quadrilateral ABCD, And according to this rule 16, the sum of those two opposite angles is equal to 180 degrees. That is to say, alpha plus beta is equal to 180 degrees. Likewise, those two angles are also defined as the opposite angles of this quadrilateral ABCD. And according to this rule 16, the sum of those two opposite angles is equal to 180 degrees. That is to say, angle 1 plus angle 2 is equal to 180 degrees. So we can actually implement rule 16 in our drawing. I'll put in our drawing this is quadrilateral PQBM that is inscribed by this circle. Therefore, according to rule 16, the sum of its two opposite angles is equal to 180 degrees. Those are the two opposite angles of this quadrilateral QBMP. Therefore, the sum of those two opposite angles must be equal to 180 degrees according to rule 16. This is angle beta, so angle beta plus the size of this angle, in total the sum of those two angles must be equal to 180 degrees. Therefore, this missing angle must be equal to 180 degrees minus beta. Why? Because 180 degrees minus beta plus beta is 180 degrees. That is the sum of the opposite angles in this quadrilateral QBMP that is inscribed by this circle. Likewise, the sum of those two opposite angles must be also equal to 180 degrees according to rule 16. But this angle equals to beta. So angle beta plus this angle, in total the sum of those two angles must be equal to 180 degrees according to rule 16. Therefore, this missing angle must be equal to 180 degrees minus beta. Why? Because 180 degrees minus beta plus beta is 180 degrees. That is the sum of the angles. That is the sum of those two opposite angles in quadrilateral PQBM that is described by this circle according to rule 16. So in total, we have found out that this is angle beta and this angle is equal to 180 degrees minus beta in its size. So 180 degrees minus beta plus beta is 180 degrees. That is the sum of those two angles. But those two angles are defined as one-sided interangles. So we have found out that the sum of those two one-sided interangles is equal to 180 degrees. And therefore, according to rule 18, those two one-sided interangles must be between parallel lines. That is to say, QB is parallel to PM. So I repeat quickly on rule 18. According to rule 18, if the sum of two one-sided interangles is equal to 180 degrees, then they are located between two parallel lines. So in the drawing, we have this is line A, this is line B, this is the red line C that intersects with those two lines at those 2 points. In addition, we have those two angles, alpha and beta, that are defined as one-sided interangles. And we know that alpha plus beta equals to 180 degrees. And because of the fact that the sum of those two one-sided interangles is equal to 180 degrees, according to this rule 18, they must be located between parallel lines. That is to say, line A is parallel to line B. So actually, we have already implemented rule 18 in our drawing. So as mentioned, the sum of those two one-sided interangles is equal to 180 degrees. Again, we put 180 degrees minus beta plus beta is 180 degrees. And therefore, those two one-sided interangles must be located between parallel lines. That is to say, QB is parallel to PM according to rule 18. So I'll write it down. QB is parallel to PM according to rule 18. So in the next step, I'll copy this semicircle with the diameter PM in a new page, and we'll continue to analyze it. So actually, this is the semicircle with the diameter PM that I copied from this drawing. PQ equals to MB equals to 10, QB equals to X, that is the line segment that we are looking for in this question. Point O is the center of this semicircle. OP equals to OM, the above the area of the circle, is equals to 15 units. So in the next step, we will join points O and Q together by a straight line. OQ is of course the radius of this circle, of the semicircle, that is equals to 15. We join points O and B together by a straight line. OB is also the radius of this semicircle, that is equals to 15 units in its length. We have already found out that according to rule 18, QB is parallel to PM. So I'll write it down. QB is parallel to PM according to rule 18. Those two angles, that is to say angle OQB and angle POQ, those two angles are defined as alternating angles, and they are located between the parallel lines QB and PM. QB is parallel to PM according to rule 18. So those two alternating angles are located between the parallel lines QB and PM, and therefore according to rule 15 they are equal to each other. So if we check on rule 15, according to rule 15, alternating angles between parallel lines are equal to each other. So in the drawing, we have line A that is parallel to line B. The red line is line C that intersects with those two parallel lines at those 2 points. Those two angles, alpha and beta, are defined as alternating angles, and because of the fact that they are located between the parallel lines A and B, A is parallel to B, they are equal to each other. That is to say, alpha equals to beta. So according to rule 15, alternating angles that are located between the parallel lines must be equal to each other. That is to say, alpha equals to beta. So we can implement rule 15 in our drawing. So as I mentioned before, those two angles are defined as alternating angles, and they are located between the parallel lines QB and PM. QB is parallel to PM. And therefore, those two angles are equal to each other according to rule 15. So if we define this angle is alpha, then this angle must be also equal to alpha because they are equal to each other according to rule 15. So in the next step, I will present to you the law of cosines, and we will implement the law of cosines in this green triangle, triangle OPO, and in this white triangle, triangle OQB. So what is the law of cosines? Actually, the law of cosines is for in any triangle. So this is triangle ABC, this could be any triangle. This is side AB, that is equals to A unity in its length. This is side AC, that is equals to B unity in its length. This is side BC, that is equals to C unity in its length. This is angle theta. According to the law of cosines, cosine theta equals to cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. Again, according to the law of cosines, cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. So in the next step, we will implement the law of cosines on this green triangle, triangle POQ. So I copy this green triangle POQ in a new page, and we will implement on it the law of cosines. So actually, this is triangle P, the green triangle POQ, the public from here, and this is angle alpha. So according to the law of cosines, in this triangle POQ, this will be equation 1. So according to the law of cosines, cosine alpha equals to 15 squared plus 15 squared minus 10 squared divided by 2 times 15 times 15. And again, according to the law of cosines, in this triangle PQO, cosine alpha equals to 15 squared plus 15 squared minus 10 squared over 2 times 15 times 15. So this is equation 1. In the next step, I copy this white triangle QOB here, and we implement the law of cosines in this white triangle. So here, this is the right triangle, QOB. I copied from this drawing. According to the law of cosines, this right triangle QOB, this is angle alpha, so this will be equation 2. Cosine alpha equals to x squared plus 15 squared minus 15 squared over 2 times x times 15. Okay, again, in this triangle QOB, according to the law of cosines, cosine alpha equals to x squared plus 15 squared minus 15 squared over 2 times x times 15. So we have two different equations for cosine alpha. So in the next step, we create equation 3 that says that cosine alpha according to equation 1 must be equal to cosine alpha according to equation 2. So according to equation 3, cosine alpha according to equation 1 must be equal to cosine alpha according to equation 2. Cosine alpha according to equation 1 equals to 15 squared plus 15 squared minus 10 squared over 2 times 15 times 15. And it must be equal to cosine alpha according to equation 2. Cosine alpha according to equation 2 equals to x squared plus 15 squared minus 15 squared over 2 times x times 15. So here, this is equation 3. According to equation 3, cosine alpha according to equation 1 is equal to cosine alpha according to equation 2. So we focus on the denominator of those two expressions. This side of the denominator we have 2 times 15, and the other side we have also 2 times 15. So 2 times 15 we get cancelled. After we cancel 2 times 15, in this side of the equation we have 15 squared plus 15 squared minus 10 squared divided by 15. In the other side of the equation we have 15 squared minus 15 squared is 0. So in the denominator we left only with x squared. So it is x squared over x. X squared over x is x. So in total we left only with x in the side of the equation. So according to equation 3, we found out that x equals to 15 squared plus 15 squared minus 10 squared over 15. So x equals to 15 squared. 15 squared is 225, so it is 225 plus 225, that is 450, minus 10 squared. 10 squared is 100, so it is minus 100 over 15. So in total we found out that x equals to 450 minus 100 is 315 over 15. Here we will divide both the numerator and the denominator of this number by 5, and we get that 350 over 5 is 70, and 15 over 5 is 3. So in total, we found out that the length of line segment QB that is equal to x is equal to either 70 over 3 units. In terms of numbers, it is equal to 23 and 30 units in its length. That is the answer to the second question. Repeat again, we found out that the length of this line segment QB that is equal to x is equal to either 70 over 3 units. In terms of numbers, this line segment QB that is equal to x is equal to 23 and 30 units. We finish with the second question. In the next step, I will summarize the lecture. We'll start with the first question, of course. Our mission in this first question is to find out the area of this circle that is described by this trapezoid ABCD. A trapezoid is a quadrilateral with one pair of parallel sides. In this trapezoid ABCD, side AD is parallel to side BC. So we have to find out the area of this circle. So first of all, we define the center of this circle. This point is point O. We define the point of tendency of tangent AD with this circle. This point is point P. And we define the point of tendency of tangent BC with this circle. This point is point Q. Here we implemented rule 2. If we focus on this convex standpoint point A, from this convex standpoint point A, we have two tangents to this circle. Tangent AP and tangent AM, and according to rule 2, they are equal to each other. That is to say, AM equals to AP. But AP is A, according to what is given in the question, therefore AP must be also equal to A units in its length. Likewise, if we focus on this convex standpoint point B, from this convex standpoint point B, we have two tangents to this circle, tangent BQ and tangent BM, and according to rule 2, they are equal to each other. That is to say, BM equals to BQ. But BM is B according to what is given in the question, therefore BQ must be also equal to B units in its length. So, in the next step, we join points O and P together by straight line. Point O is the center of the circle, point P is the point of the point of the second step, therefore OP is the radius of this circle. We define the radius of this circle is x, so OP equals to x. And because of the fact that the radius OP is equals to x, the radius OP is drawn to point P, that is the point of tendency of tangent AD with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AD will be perpendicular to the radius PO. If AD is perpendicular to PO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and Q together by straight line. OQ is the radius of this circle that is equals to x. And because of the fact that the radius OQ that is equals to x, the radius OQ is drawn to point Q, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius QO. If BC is perpendicular to QO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. In the next step, we did the construction, that is to say, from this point A, we go perpendicular on BC. Again, from point A, we go perpendicular on BC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to our construction. We define the touching point of the perpendicular from point A and BC. This point is point N. By doing this construction, we can do those two angles are defined as one-sided interangles, and are located between the parallel lines AD and BC. Why AD is parallel to BC? Because of the fact that ABCD is a trapezoid. So those two one-sided interangles are located between the parallel lines AD and BC, and therefore the sum of those two one-sided interangles is equal to 180 degrees according to rule 17. but this angle equals to 90 degrees. So 90 degrees plus the sides of this missing angle, in total the sum of those two angles must be equal to 180 degrees according to rule 17. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we did another construction, that is to say, from this point O, we go perpendicular on AN. Again, from point O, we go perpendicular on AN. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AN. This point is point T. When doing this construction, we can derive the small quadrilateral APOT. Inside this quadrilateral APOT, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. Likewise, inside the lower quadrilateral TOQN, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle in total must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So in total, we found out that the big angle POQ is equal to 90 degrees plus 90 degrees, that is 180 degrees. The big angle POQ is equal to 180 degrees. We know that any angle that is equal to 180 degrees in its size, it is defined as a straight line. So POQ is a straight line. Line segment POQ is a straight line. If POQ is a straight line, then PQ is also a straight line. PQ is a straight line, and therefore shape APQN has 4 sides. 1, 2, 3, 4. Do it again. Shape APQN has 4 sides, and therefore shape APQN is a quadrilateral. Shape APQN is a quadrilateral. But quadrilateral APQN has 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to this quadrilateral APQN as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So an rectangle APQN, side AP must be equal to the opposite side QN. But AP is 8, therefore QN, the opposite side QN, must be also equal to a unit in its length. Likewise, according to the sum rule, in the sum rectangle APQN, side PQ must be equal to the opposite side AN. But PQ is x plus x, it is 2x. Therefore, the opposite side AN must be also equal to 2x units in its length. What is the length of this missing line segment BN? BN equals to BQ minus NQ. And again, BN equals to BQ minus NQ. So BN equals to BQ. BQ is B minus NQ. NQ is A. So in total, BN equals to B minus A. It's BN equals to A. AN equals to 2x. And AB equals to A plus B. So in the next step, I complete the right triangle A and B in a new page. And we implemented the Pythagoras theorem on this right triangle, triangle A and B. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the sides of the perpendicular. So this is the right triangle A and B that according to the original drawing. In this right triangle A and B, AB squared, that is the square of the hypotenuse, equals to AN squared plus NB squared. AB is A plus B or B plus A. Therefore, AB squared is A plus B squared. And it is equal to AN squared. AN is 2x, therefore AN squared is 2x squared plus BN squared. BN is B minus A, therefore BN squared is B minus A squared. We open the brackets on both sides of this equation and finally found out that A plus B squared equals to A squared plus B squared plus 2 times A times B, and it is equal to 2x squared plus B minus A. B minus A equals B minus A squared equals to B squared plus A squared plus 2 times A times B. So here we have A squared on both sides of this equation, so A squared will get cancelled, and we also have B squared on both sides of this equation, so B squared also will get cancelled. After you cancel those two expressions, On this side of the equation we left only with 2ab, while on the other side of the equation we left with 4x squared plus 2ab. So total we found out that 2ab equals to 4x squared minus 2ab. Here we added 2ab to this equation, so 2ab plus 2ab is 4ab, so 4ab equals to 4x squared. Here we divided this equation by 4 and finally found out that ab equals to 4ab over 4 is ab, and it is equals to 4x squared over 4 is x squared. So in total we found out that x squared equals to ab. Our mission is to find out the area of this circle. Actually, we know that the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of this circle, our circle, must be equal to pi times the radius of this circle squared. But the radius of this circle is x. Therefore, the radius squared is x squared. So in total, the area of this circle must be equal to pi x squared. The area of our circle must be equal to pi x squared. We just right now found out that x squared equals to ab, so we substitute x squared by ab. And we found out that the area of this circle is equal to pi times ab square units. We finished with the first question. In the next step, I will answer to you the second question and solve the second question of this lecture. Our mission in this second question is to find out the length of this isolated cubit is equal to x. We have to find out the value of x. So in the original drawing we had this semicircle. This is called PA, this is equal to 10 units in itself. This is called cubit, it is also equal to 10 units in itself. This is 970 AB, this is equal to 30 units in itself. AB is the diameter of this semicircle, and it is equal to 30 units in itself. If the diameter is 30, the radius must be equal to half of it. This is to say the radius must be equal to 30 over 2, that is 15. We defined, so the radius of this semicircle is 15. We define the center of this semicircle, this point is point O, and we join points O and N. Actually, we have point O is the center of the circle, point A is the point of the circle itself, on the semicircle itself, therefore OA is the radius of this semicircle, that is 15. OB is also the radius of this semicircle, that is 15. We join points O and P together by a straight line. OP is of course also the radius of this semicircle, that is 15. In the next step, we completed this semicircle to a circle, and we extended the radius PO of this semicircle by a straight line until it touches the circle at this point. We define the touching point of the extended radius PO with this circle. This point is point M. OM is of course the radius of this circle, that is equal to 15 units in its length. We join points B and M together by a straight line. Those two angles are defined as vertex angles, when we know that vertex angles are equal to each other. So this is angle theta, and then this angle must be also equal to theta because they are equal to each other according to the rule that I mentioned. In the next step, we prove that this triangle POA can go into this triangle OBM. So why those two triangles can go into each other? First of all, side PO of triangle APO is equal to side OM of this triangle OMB. They are both the area of the circle, and therefore they are equal to each other. In addition, those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. And finally, side AO of triangle APO is equal to side OB of triangle OMB. They are both the area of the circle, and therefore they are equal to each other. So if we prove that those two triangles can go into each other according to side angle side rule. That is to say, we have those two sides, and the angle that is included between those two sides in this triangle POA are correspondingly equal to those two sides, and the angle that is included between those two sides in this triangle MOB. And therefore those two triangles can go into each other according to side angle side rule. And from the fact that those two triangles can go into each other, we will derive that side PA of triangle AQO is equal to side VM of this triangle OMB. PA equals to BM. But it is given us the question that PA equals to 10. So we can write here that PA equals to 10, and from this equation 10 equals to PA equals to BM, we will derive that BM is also equal to 10 units in its length. This is side BM, that is equal to 10 units in its length. This is chord PM. Chord PM passes from point O, that is the center of the circle, and we know that any chord that passes through the center of the circle must be the diameter of the circle. So PM is the diameter of this circle. So in the next step, I copy this semicircle with the diameter PM, and we analyze this semicircle. So this is the semicircle with the diameter PM that I copy from original drawing. Point O is the center of this semicircle. PB equals to MB equals to 10. They are equal to each other in their lengths. So, and this is QB, this is equal to X units in its length. That is the line segment that we are looking for in this question. So, in the next step, we extended PB and MB by straight line until they intersect with each other at this point E. And we have the rule that if you extend two line segments that are equal to each other in their lengths, then the new line segments that will be created must be also equal to each other in their lengths. So we extended PQ and MB that are equal to each other in their lengths. And the new line segment that will be created, the new line segment that's created by extended PQ and MB are PE and ME. And according to the new rule that I mentioned, PE must be also equal to ME. The new line segment PE and ME must be also equal to each other in their lengths. So PE equals to EM according to the new rule that I mentioned. Okay, so in triangle PEM, side PE is equal to side EM. And therefore this triangle PEM is an isosceles triangle. The base of this isosceles triangle is PM. Those two angles are defined the angle of the base and of this isosceles triangle PEM, and therefore they are equal to each other. Anyway, I proved in another proof that those two angles must be also equal to each other. Why those two angles are equal to each other? Because of the fact that we have the rule that in front of equal sides in the triangle there are equal angles. And PE equals to EM. So in front of PE we have this angle, in front of this side EM we have this angle. And because of the fact that those two angles are located in front of those two equal sides, they must be also equal to each other in their sizes. So if the size of this angle is beta, then the size of this angle must be also equal to each other, to beta, because they must be equal to each other according to the rule that I mentioned. So those two angles are both equal to beta. In the next step, I completed this semicircle to a circle. So in the drawing we have, this is quadrilateral PQBM that is inscribed by this circle. And according to rule 16, any quadrilateral that is inscribed by a circle, its two opposite angles must be equal to 180 degrees. So in this quadrilateral PQBM, those two opposite angles must be equal to 180 degrees. But this is angle beta, so angle beta plus the size of this missing angle, in total the sum of those two angles must be equal to 180 degrees according to rule 16. Therefore this missing angle must be equal to 180 degrees minus beta. Why? Because 180 degrees minus beta plus beta is 180 degrees. It is the sum of the angles on this quadrilateral PQBM. The sum of the opposite angles on this quadrilateral PQBM that is inscribed by this circle. Likewise, the sum of those two opposite angles must be also equal to 180 degrees according to rule 16. But this is angle beta, therefore this missing angle This missing angle must be equal to 180 degrees minus beta. Why? Because 180 degrees minus beta plus beta is 180 degrees. That is the sum of the angles. That is the sum of the opposite angles in this quadrilateral PQBM that is inscribed by this circle according to Rule 16. So in total, we found out that this is angle beta and this angle equals to 180 degrees minus beta in its size. The sum of those two angles is 180 degrees. Why? Because 180 degrees minus beta plus beta is 180 degrees. But those two angles are defined as one-sided interangles. So we found out that the sum of those two one-sided interangles is equal to 180 degrees. And therefore, according to Rule 18, they are located between two parallel lines. That is to say, QB is parallel to PM. Again, QB is parallel to PM according to Rule 18. So in the next step, I copied this semicircle with the diameter PM and we continue to analyze it. So okay, this is the semicircle with the diameter PM that I copied from this drawing. And point O is the center of the semicircle. PQ equals to MB, they are both equal to 10 units in its length. OP equals to OM equals to OB equals to OQ, they are both the radii of this semicircle is equals to 15 units in its length. And finally, QB equals to X, that is line segment that we are looking for in this question. We have already found out that according to Rule 18, QB is parallel to PM. Again, QB is parallel to PM according to Rule 18. So actually, those two angles are defined as alternating angles and they are located between the parallels QB and PM. Therefore, according to Rule 15, they are equal to each other. According to Rule 15, alternating angles between parallel lines are equal to each other. So those two alternating angles that are located between the parallel lines QB and PM are equal to each other. So if this is the angle alpha, then this angle must be also equal to alpha because they are equal to each other according to Rule 15. So in the next step, I presented to you the law of cosines and we implemented the law of cosines in this right triangle QPO and in this right triangle OBQBO. So what is the law of cosines? The law of cosines is to an n triangle. This is triangle ABC, this could be any triangle. And this triangle ABC, side AB equals to n units length, side AC equals to B units length, side BC equals to C units length. This is again theta according to the law of cosines. In this triangle ABC, cosine theta equals to A square plus B square minus C square over 2 times A times B. We implemented the law of cosines in the great triangle QPO. So I copied the great triangle QPO here and implemented the law of cosines in this triangle QPO. This is again alpha, so in this triangle POQ, according to the law of cosines, cosine alpha equals to 15 square plus 15 square minus 10 square over 2 times 15 times 15. Again, cosine alpha according to the law of cosines in this triangle POQ equals to 15 square plus 15 square minus 10 square over 2 times 15 times 15. In the next step, I copied the white triangle QOB here and implemented the law of cosines in this right triangle QOB. According to the law of cosines, cosine alpha equals to x square plus 15 square minus 15 square over 2 times 15 times x. Again, cosine alpha in this triangle QOB is equal to x square plus 15 square minus 15 square over 2 times x times 15. So we have two different equations for cosine alpha. Therefore, we created equation 3 that states that cosine alpha according to equation 1 must be equal to cosine alpha according to equation 2. Again, according to equation 3, cosine alpha according to equation 1 must be equal to cosine alpha according to equation 2. Cosine alpha according to equation 1 equals to 15 square plus 15 square minus 10 square over 2 times 15 times 15. and it must be equal to cosine alpha according to equation 2. Cosine alpha according to equation 2 equals to x squared plus 15 squared minus 15 squared over 2 times x times 15. So we have 2 times 15 on both sides of the denominator of those two expressions, so 2 times 15 will get cancelled. After we cancel 2 times 15, in this side of the equation we have 15 squared minus 15 squared, that is 0. So in total we left only with x squared over x, that is x. So in total, this side of the equation we left only with x. While on the other side of this equation 3, we left with 15 squared plus 15 squared minus 10 squared over 15. So in total, according to equation 3, we actually found out that x equals to 15 squared plus 15 squared minus 10 squared over 15. So x equals to 15 squared is 225, so 225 plus 225 is 450, minus 10 squared. 10 squared is 100, so it is minus 100. So it is 450 minus 100 over 15. 450 minus 100 is 350, so in total this expression equals to 350 over 15. So in total we found out that x equals to 350 over 15. We divided both the numerator and the denominator of this expression by 5, and we found out that 350 over 5 is 70. And 15 over 5 is 3. So if we found out that the length of line 7 cubed is equal to x, it is equal to either 70 over 300 in itself, or in terms of numbers, the length of this line 7 cubed, the length of this line 7 cubed is equal to x, is equal to 23 and per unit in its length. Okay, thank you very much.